In this video, we're going to start to look at some of the different aspects of chemical reactions. In a chemical reaction, the atoms and or the molecules involved are rearranged until they form new combinations. And so remember when we talked about chemical change a while ago, in a chemical change, we have new compounds that didn't exist before that have new properties. Chemical changes take place by way of chemical reactions. Whatever we had in the beginning, the compounds or elements that do the reacting are called reactants. And the compounds or elements that are produced are called our products. So just a little bit of terminology that we're going to use throughout this discussion. It's important to note that every atom that was in the reactants also appears in the products. It's only the bonds and the combinations that have been changed. No atoms have been created and no atoms have been destroyed. The law of conservation of mass is always followed. Matter cannot be created or destroyed. And so let's look at some of the pieces of a chemical reaction, or chemical equation, rather. In a chemical equation, we show the reactants and the products in a reaction. We also show the relative amounts. And so sometimes I think of this as the recipe. And so in this example here, we have aluminum plus oxygen to form aluminum oxide. This tells us that we're going to need 4 aluminum atoms to come together with 3 O2 molecules, and that will form 2 aluminum oxide molecules. And we're going to look at where some of these numbers come from in a little bit. These numbers in front are called our stoichiometric coefficients. We have to note that our product here follows the rules that we've already talked about. When aluminum and oxygen come together to form a compound, so aluminum, remember, with its 3 plus charge, oxygen with its 2 minus charge, when the two of those come together to form a compound, the chemical formula for that is going to be Al2O3. And that, in fact, is the formula that we see here. But aluminum started out by itself, started out as just Al. Oxygen started out as O2, because this oxygen is something that we call a diatomic molecule, which we're going to talk about on the very next slide. And so our numbers here, our subscripts, end up being very different, because again, we must follow the rules when aluminum and oxygen come together of what their chemical formula is going to be. And so that leads us to these stoichiometric coefficients, which we're going to talk about in just a second. In order to start this discussion, we do have to mention diatomic molecules, which I just mentioned in reference to oxygen. Diatomic molecules are elements that when they do exist by themselves, they always exist as one of them bonded to another one. And so the oxygen that we breathe, it's not just single oxygen atoms. It's always one oxygen atom bonded to another one in the form of O2. So 2 oxygens bound together. And these 7 different atoms all do that, or different elements all do that same thing. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. One of the easy ways to remember this, or easier ways, because you do just have to sort of know these as well, I mean, just sort of remember that hydrogen does it. But then the other ones that do sort of form a number 7 right here. They start with nitrogen and then over to the halogens and then down. And so all of those plus hydrogen are our diatomic molecules. And so the reason that I bring this up now is let's talk about, and we're going to see where these stoichiometric coefficients come from that I talked about. Let's talk about, there we go. Let's talk about the formation of water. And so we've written a chemical equation here to describe the formation of a water molecule. Hydrogen has to come together with oxygen. We know that hydrogen is a diatomic, so when it's by itself, it must exist as H2. Oxygen is also a diatomic, so when it exists by itself, it must exist as O2. They're going to come together to form water. We also know that the chemical formula for water is H2O. And that's non-negotiable. That's just the very definition of water. That's what water is. But now let's look at our conservation of mass. We started out with 2 hydrogens, and we still have 2 hydrogens. So that's good. We started out with 2 oxygens, but now we only have 1 oxygen. Law of conservation of matter tells us that cannot happen. Atoms cannot be created or destroyed. So we can't just lose an oxygen. And so what we say, we do a little count here. We say that the oxygen atoms are what we call not balanced. We don't have the same number on both sides. And so a logical question, something a lot of people wonder about at this point is, well, can't I just add a no to the products? Can I just do this, H2O2? Makes sense, right? Now I've got 2 of each. It looks like I have the same number. Law of conservation of mass is happy. There we go. No, 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 no. That's a totally different molecule. H2O2 is not water. So you cannot just arbitrarily change the chemical formula, because by changing that chemical formula, you've changed what it is, and we cannot do that. What we can do is change the number of water molecules that we make. If I make a whole additional water molecule instead, if I say that instead of 1 water molecule, I'm going to make 2, now I've got 2 oxygens. Look at that. However, now I've formed 4 hydrogens, but I only started with 2. So I'm going to say that I start instead with 2 H2 molecules. Now I have a balanced equation. Now this equation tells me that in order for hydrogen and oxygen to come together to form water, I'm going to need to take 2 H2s plus 1 O2, and that's going to give me 2 H2Os. That is what is known as balancing an equation. Let's look at this example here. Sodium chloride plus magnesium bromide. So again, though, let's see why our subscripts are different on each side. When sodium and chlorine come together to form a compound, we have Na1 plus and Cl1 minus, and so that's going to be NaCl. Magnesium and bromine, magnesium 2 plus and Br1 minus, MgBr2. Now these two are going to react, and what's going to happen, and we'll look in more detail at this in the next video when we talk about reaction types, but what's going to happen is that in my chemical reaction, Na is going to come together with Br, and Mg is going to come together with Cl. And so in my new products, I now have Na1 plus coming together with Br1 minus for chemical formula of NaBr. I also have Mg2 plus coming together with Cl1 minus for chemical formula of MgCl2. And so we can see that our subscripts between our reactants and our products are different, which leads us to having to then balance the equation using stoichiometric coefficients in front to satisfy the law of conservation of matter. So we just count. We start off by literally just counting. And so to start off, I've got 1 Na on my reactant side. I've got 1 Mg. I've got 1 Na on my product side and 1 Mg, looking good so far. 1 Cl on my reactant side, 2 Brs, 1 Br on my product side, and 2 Cls. So that's not balanced. Again, the temptation is to do this, but you cannot do that. As we've already seen here, those are not the chemical formulas for when Na comes together with Cl or when Na comes together with Br. So you cannot simply add a subscript like that. What we can do is change how many of each we have. We can say instead that I'm going to start with 2 NaCls, and I'm going to create 2 NaBrs. That now balances the equation for us. So when we balance equations, once the equation is written out, The subscripts of the products or reactants cannot change. Once you figured out what those are, those don't change. What can change is the coefficients in front to satisfy the law of conservation of mass, and we call that balancing a chemical equation. So here's another example here. 1 methane, 1 CH4 plus O2 gives us CO2 plus H2O. So see what you can do with this. Try to pause the video now. Try to balance this equation. See what you get. Hopefully you got this. And so your basic steps in writing a balanced chemical equation is you're going to write out the equation using the formulas and the rules for formulas that we've talked about. And then you're going to balance the compound with the most elements in the formula first. And so this is just sort of a general guideline, is to look for the compound that has the most elements in it and balance that in other areas. Anything that's on its own, so such as in this one, O2 was by itself, save that for last. That's usually easiest. Check to see that the sum of each individual element is equal on both sides. I mean, ultimately, what you're trying to do here, your big goal in balancing a chemical equation, is to ensure that there is the same number of each type of element on both sides of the equation. That's your goal. And so a chemical reaction is balanced when that happens. So we can see in this case, now we have, there we go. Now that this one is balanced, we have 1 carbon over here, 1 carbon over here. 4 hydrogens on our reactant side, 4 hydrogens total on our product side. 4 oxygens on our reactant side, 1, 2, 3, 4 oxygens on our product side. So this is now a balanced equation. I realize that you can't see this looking at your screen here, but in the, if you go to the lecture video, you'll be able to see this slide, or the PowerPoints rather, the slides. You'll be able to see this. And these are some general guidelines and general tips and hints. Often though, it's just sort of a game of going back and forth. You find something that's not balanced, something that's out of whack, put a number in front and fix it. That might change something else that you have to go back and fix. And you kind of keep going back and forth with that a little bit until you come up with a correctly balanced equation. And so some other, just sort of some practice. And so for instance, this one here, we're going to balance 1 atom type at a time. So we're going to start with something found. Oh, this is frustrating, my mouse. So for instance, here we're going to start with our carbon. We're going to leave O for last because it's by itself. But we see that we have 6 carbons here on our reactant side, only 1 on our product side. So we're going to go ahead and place a 6 in front of this CO2. That balances out our carbon for us. Now we want to fix our hydrogens. 4 hydrogens in our reactant side, 2 in the H2 over here. So we're going to put a 7 in front of our H2O. And that will take care of our hydrogens for us. And so now we see for oxygens, we have 12, 19 oxygens over here. And so what we want to do, and this is sort of just a placeholder, since oxygen is diatomic, so we need to come up with 19 on our reactant side. Oxygen is diatomic, so it has to exist as O2. So what we can place in there for now is just say 19 halves. Now we can't leave it that way. We can't leave something as a half. So if you get to this point, then you just go through and multiply everything through by 2, and then we get a correctly balanced equation. Okay, that was about all I wanted to say there. Let's look at a couple of quick examples, actually. Let me pull up, here is our course website. Let's pull up, a practice worksheet on balancing equations. And so we're right here now in our chemical quantities and chemical reactions. Go to my materials page. I must have some practice balancing. Here we go. Balancing equations practice. Let's go ahead and do, we'll end up doing a couple of these maybe, but let's do number 6. So KClO3. I just got a message saying my Apple Pencil is low. Hopefully I'll have enough time left in it to do this. But KClO3. Okay, just wanted to write out my reaction. So we're going to do this one here. And so we go through first, and there's a number of ways to go about this. Well, we can see that, okay, 1K on our reactant side, 1K product, that's okay. 1Cl, 1Cl, that's okay. 3 O2s, or 3 oxygens, but 2 oxygens. So we can see that there's no real easy way to necessarily fix this, but what I can do is if I have 3 O2s and 2 of these, that now gives me 6 oxygens on both sides. So there we go, my oxygen's taken care of, but that messed up my potassium and my chlorine. So what I can do though is put a 2 right here, and that takes care of it. That's now a balanced equation. Let's look at one more. Let's look at number 3. We have AlNO3 plus NaOH. Gives us AlOH3 plus NaNO3. Now, another advantage in memorizing your polyatomic ions is that you can treat them as one whole thing when you're balancing. And so rather than going through this one and saying 1 Al and I have 3 Ns and 9 Os, I'm going to recognize that NO3 is a polyatomic ion, and I'm going to treat it as one entity when I'm balancing my reaction. And so I'm going to say that I have 1 Al and 1 Al, so that's okay. I have 3 NO3s. I have 1 NO3. And so I'm going to go ahead and fix that whole thing by putting a 3 in front of my NaNO3. That messed with my number of NAs. Now I have 3 NAs, 3 sodiums on my product side. So I'm going to say that I'm going to put a 3 in front of my NaOH. Look what that did to my OHs. Now I have 3 OHs here, but I have 3 OHs here. And so that fixed it for me. And so now this is balanced. So I definitely encourage you to try all these practice, go through the practice exercises and try to balance those. And now I'm just going to, before we move on to the next topic in this video of some stoichiometry calculations, I am just going to take a quick pause. So there'll be a little glitch in the matrix here as I pause us and I charge up my Apple Pencil. And we are back with a charged up Apple Pencil now. Okay. So from a balanced equation, one of the things that we can do is we can use that to start looking at the amounts of chemicals involved in a chemical reaction. These are called stoichiometry calculations. And they're made possible because the coefficients in a balanced equation give us the molar ratio between the reactants and the products. And so for instance, actually we'll look at an example in a second, but we can do a number of different things with a balanced chemical equation. We can look at the maximum number of moles of product form from a given number of moles of reactant. And we can also look at the maximum mass of a product formed from the mass of a reactant. And we'll look at examples of these. So here we see the reaction between ethanol and oxygen. It's a combustion reaction. And so C2H6O plus 3 O2s give us 2 CO2s and 3 H2Os. We're going to now start looking at these coefficients in front as the number of moles. And so 1 mole of ethanol plus 3 moles of O2 give us 2 moles of CO2 and 3 moles of H2O. And that provides for us a number of different conversion factors that we can use in converting between one and the other. And so if we want to know, for instance, how many moles of oxygen we need to react with 5 moles of ethanol. Then again, we're going to look at our conversion factors here. We're going to treat our coefficients in front as nothing more than conversion factors between one and the other. And so we can either think of this as 1 mole of ethanol to 3 moles of oxygen, or 3 moles of oxygen to 1 mole of ethanol. And so we would set this up, we would use this conversion factor however we needed to in our given reaction or whatever we were looking for. So in this example here, we're told that we have 5 moles of ethanol. So we want to set up our conversion factor the second way so that moles of ethanol cancel out. And we can see, in fact, that we're left with 3 times 5 for 15 moles of oxygen. And so if I start with 3 moles of ethanol, I'm going to need 15 moles of O2. It's important to note, too, that the balanced chemical equation just gives us the basic recipe. What are my ratios here? In any given reaction that you run, you will use different amounts, but they're always going to react in those same ratios, and that's the important piece. So we can look at another example here. Iodine and fluorine react to form iodine trifluoride. First thing we want to do is write out our chemical equation for this. I2 plus F2, remember iodine and fluorine, both diatomics, form IF3, there's our iodine trifluoride. Then we need to balance that equation. So now we see our correctly balanced equation. And so we can see that we have a number of different stoichiometric ratios from that. 1I2 to 3 F2s, 1I2 to 2 IF3s, 3 F2s to 2 IF3s. And so we have those 3 different ratios we could use depending on what we were looking for. And any of those we can use in the way that we need to, either as written or flipped, depending on how we need things to cancel out in our dimensional analysis setup. So now let's look at some basic types of calculations that we would do with this. Let's say, for instance, you're told that you have 2 grams of a particular reactant, and you want to know how many grams of a particular product you're going to make from that. This gives us our steps that we're going to take in order to do that calculation. The first thing we're going to do is use our molar mass to convert whatever amount that we're given over to moles. We're then going to use our coefficients from our equation. We're going to use our stoichiometric ratios to convert from moles of whatever it is we were given for information to moles of whatever thing that we're looking for. And then finally use the molar mass of that new compound in order to find the mass of that compound. And this just writes that out in steps. We're going to convert the mass of whatever we're given to moles using our molar mass. We're going to convert the moles of whatever we're given to moles of whatever's being asked for using our molar ratios. And then finally convert from moles of what is being asked for to grams using our molar mass. So an example here, we're starting with 8.32 grams of methane. We want to know a couple things. We want to know maybe how much O2 is used up. And then we could also calculate how much CO2 and H2O are actually formed. And so let's look at those steps for the first one first. Let's look at how much O2 is used. First thing we're going to do is use molar mass to convert those grams of O2 we were given to moles of O2. Sorry, CH4. We started with 8.32 grams of CH4, so we're going to use our molar mass and convert that to moles of CH4. Next, we're going to use our molar ratio to convert to the moles of O2. And then finally, so now that we know how many moles of O2 we need, we're going to use our molar mass of O2 to convert to grams of O2. So we can see that if we start with 8.32 grams of CH4, we're going to need 33.3 grams of O2. What I would recommend is that you try the other two questions that we had, go through the same process, but calculate also how much CO2 is going to be formed and how much H2O is going to be formed. Try those calculations out. You're going to use the same basic steps. In fact, this first step will be the exact same. But in this step here, you're going to have different stoichiometric ratios, and then you're obviously going to have different molar masses depending on which product that you're looking for. So try those out. But those are basic, what we call stoichiometric calculations. And again, there's lots of practice on the website. Those are listed right here under mass problems. You have a whole bunch of different practice problems of those. And so I would try those out. They're good practice. You have the answer key available to you. And so with that being said, that is all of our video on reactions. And so stay classy, USM.